All right, let's dive into a physics puzzle that's had scientists totally stumped for decades. It's a real mystery, but the solution might be surprisingly simple. And it could completely change the future of energy. Let's get right into it. Okay, so get this. It all starts with a question that just seems to break the laws of common sense. You're trying to heat something up, this super hot gas called a plasma. So you pump in more power, and it gets colder. How is that even possible? This one single baffling observation? Well, it's right at the heart of our story. So here's the deal. There's this huge gap between what we think should happen and what actually happens in the lab. On one hand, simple logic, right? You put more power in, you should get more heat out. But the reality that scientists see all over the world, it's anything but simple. It's chaotic, it's unpredictable, and sometimes it's completely backwards. And that brings us to our first section, the plasma heating puzzle. We're going to explore this really strange behavior that our standard physics models have had a very hard time explaining. Now, why does any of this even matter? Well, because plasma is the key ingredient for fusion energy. You know, the same thing that powers the sun. If we can build a fusion reactor here on Earth, we're talking about clean, practically limitless energy. But to do that, you have to control and heat plasma to millions of degrees. And that's where things get weird. So let's really dig into the specific things our current models just can't handle. These are the unsolved mysteries that have left physicists just scratching their heads for years. First up is the mystery of the sudden heating threshold. You'd think heating something up would be a nice, smooth process. Turns out, not so much. Imagine you're turning up a dimmer switch on a light. Standard physics says the light should get smoothly and predictably brighter. But in these plasma experiments, scientists crank up the power and nothing happens. They crank it more, still nothing. And then, bam, the plasma just suddenly ignites with heat. It's like a switch just flips on, and our linear theories just have no good way to explain that jump. The second mystery is just as strange. It's a classic whodunit. Where in the world did all the energy go? And this number? Wow. It really shows you the scale of the problem. In some experiments, scientists will pump in megawatts of power, and up to 90% of it just vanishes. Poof! It never even reaches the plasma. One day, the system absorbs almost all the energy, and the very next day, with the exact same setup, it might only absorb 10%. Our current models just can't predict this massive, unpredictable loss. And that brings us to the third, and honestly, the most counterintuitive mystery of them all, this thing called the anti-resonance effect. Yeah, this is the one we started with. More power in, less heat out. It's a direct contradiction of what should happen, and it's been seen in fusion experiments. It's kind of like pushing the gas pedal on your car and having it slow down. It makes no sense, and our standard models, they just don't have a mechanism for it. So we have these deep, deep mysteries. But what if the solution isn't about brute force? What if it's all about something more subtle, like timing and rhythm? Let's move on and see how a new theory based on waves tries to make sense of all this chaos. This new idea is called the Harmonic Scale Framework, or HSF. Now, so what we're talking about today, all you really need to know is that it says this seemingly chaotic behavior isn't actually chaos at all. It's all governed by a very precise interaction, a coupling, between two different kinds of waves. And here they are, the two key players in this story. On one side, you've got K2 waves. Just think of these as the external push. The microwaves are radio waves that we're beaming in from an antenna to try and heat things up. And on the other side, you have K3 waves. That's the plasma's own internal rhythm. It's natural vibrations. The whole theory says everything depends on how these two decide to dance together. You know, what's so cool about this is how simple the core idea is. It's just like pushing a child on a swing. If your external push is timed perfectly with the swing's natural rhythm, the child goes higher and higher. You're transferring energy super efficiently. But if your timing is off, you end up fighting the swing. It gets messy, and you might even slow it down. It really is all about the timing.
So let's connect this back to our mysteries. How does this simple idea of waves and timing actually solve the plasma puzzle?
This slide lays out the two big outcomes perfectly, using our swing analogy. First, you've got constructive coupling. That's the perfect push. The external waves and the internal rhythm are totally in sync. They amplify each other, and you dump a massive amount of energy in. That's your sudden heating. But then you have destructive coupling, the badly timed push.
The waves are out of sync, they clash, they cancel each other out, and this doesn't just fail to add heat, it can actually push energy back out, which explains that bizarre cooling effect. So here's the payoff. That sudden heating threshold, HSF says that only happens when your external push gets strong enough to lock onto the plasma's internal rhythm. The missing power? Well, that's what happens when your push accidentally excites the wrong rhythm, sending energy somewhere else entirely. And the anti-resonance, the cooling, that's when your push is perfectly out of sync with the swing, actively fighting against it and pulling energy out of the system. All of a sudden, the chaos starts to look like a predictable system. But look, a good story isn't enough in science, right? The real question is, can we actually test this? Is this just a nice idea, or is it a real falsifiable theory? And according to the physicists behind this theory, the answer is a huge yes. The whole framework is built on this core principle. Everything has to be testable. This isn't philosophy. If you can't design an experiment to try and prove it wrong, it isn't science. So what that means is, the theory makes these very concrete, measurable predictions. It says there will be a sharp power threshold that you can find. It says those weird cooling dips have to be observable under specific conditions. It even makes precise mathematical predictions about power and geometry. These are all things scientists can go into a lab and test right now to see if the theory actually holds up. And this really shows the rigor behind it. Now look, you don't need to be a physicist or understand what all these symbols mean. The point of showing you a formula like this is to demonstrate that this isn't just a vague concept of rhythm. It's a fully baked mathematical framework that makes very precise quantitative predictions about how something like the antenna's angle, that's a little phi symbol, is going to affect the heating power. Which brings us to the big finale. Why does solving this one very specific physics puzzle matter so much to all of us? Because think about it. If this theory is correct, if all that chaos we see in fusion experiments is really just a predictable dance of waves, it could change everything. It would give us a roadmap to design way more efficient heating systems, to avoid that missing power, and to finally get precise control over the heart of a fusion reactor. The key to clean, limitless energy might not be about more power after all, but simply better timing.